In this video, we're going to take a look at subspaces and dimension. So first thing we can do is define what a subspace is. So we'll say that a subspace of Rn is a collection of vectors, let's call it S. So it's just a set of vectors S in Rn such that three properties are true. So first property is that the zero vector should be in the set S. Second property is that if you grab any vector that's in S, then all the multiples of that vector should also be in S. Third property is that if you take any two vectors, choose any two vectors that are in your set, then their sum should also be in that set S. So let's look at a few visual or geometric examples of what subspaces of our Rn can look like. So let's call these examples here, let's call them A, B, and C. Three classic examples of subspaces of Rn. So example A, any line through the origin in R2 is a subspace of R2. So let's try to understand why that should be true. So we've got this line through the origin, contains the zero vector because it goes through the origin. So definitely property 1 is satisfied. If you choose any vector that lies along that line, certainly all the multiples of the vector are also contained in this set. And if you grab any two vectors along this line, let's indicate two blue vectors here. If you sum them together, you'll end up with something that is also lying along that same line. So in other words, if you take any two vectors u and v in this set and you add them together, you're getting another vector that's still in this set. So any line through the origin in R2 is a subspace of R2. Similarly, any line through the origin in R3 is a subspace of R3. And another classic example is if you take a plane through the origin in R3, you can check that that's a subspace of R3. So in particular, let's look at property 3 for this plane. So imagine that you take any two vectors that lie on this plane. We're going to add them together. So we know from addition of vectors that the sum is going to look something like this big blue vector here. And that's certainly still on that plane through the origin. So now that we've seen the definition of a subspace, let's see how to easily recognize whether a set of vectors is a subspace. So here's our fact. A set of vectors S is a subspace of Rn if and only if our set S can be written as the span of a set of vectors. It could be the span of a single vector, or it could be the span of multiple vectors, depending on the specific example. So if you want to figure out whether a set is a subspace, figure out whether you can write it as a span. If you can, if it's a subspace. If you cannot write it as a span, then it's not a subspace. So let's do a couple of examples to investigate that. So here's our question. We want to know whether this set is a subspace of R3. The set is the set of vectors x, y, z such that 3x plus 4y plus z equals 0. So we're going to try to describe this as a span. And the trick for these type of problems is to start off with whatever your restriction is and see if you can solve for one of the variables. So we're just going to take this 3x plus 4y plus z equals 0. We're going to solve for z. So that's like saying z has to equal negative 3x minus 4y. And that way we can rephrase our set of vectors as saying, well, it's a set of vectors x, y, z such that this restriction is true. So such that z equals negative 3x minus 4y. But once you write it like that, there's actually a much cleaner way of describing that set. See, we could just replace the z with this restriction that we've just figured out. So we could just put the minus 3x minus 4y right in there. And then we're saying, okay, it's a set of vectors in R3 that look like this. First two components can be anything, but the third component is then forced once we know what the first two components are. So we're going to see if we can describe this as a span. So let's rewrite this a little bit. Let's say that's the same thing as the vector x, 0, negative 3x plus the vector 0, y, negative 4y. So we're just rewriting that as a sum of things that involve x and things that involve y. And then we're going to be able to pull out our variables. So we can say that's really the set of vectors that look like x times 1, 0, negative 3 plus y times 0, 1, negative 4. Okay, and then let's remember what a span is. So a span is a set of all linear combinations of one or more vectors. So we can say this set that we've just written down, that really is the span of 1, 0, negative 3, 0, 1, negative 4. So the question was the set that we started with a subspace? And the answer is yes, because we were able to describe it as a span of one or more vectors, in this case, span of 2 vectors. So now we're going to see an example of a set that's not a subspace of Rn. So we want to decide whether the following is a subspace of R3, and the set that we're given is a set of vectors x, y, z, such that z equals x plus 1. So let's try our strategy of solving for one of our variables. In fact, that's already done for us, and just replacing that variable in the description of the vector. So instead of saying set of vectors x, y, z, we'll just say set of vectors x, y, x plus 1, so that we've built that restriction right into our vector. So now we need to decide whether this can be written as a span of one or more vectors. So let's do a little bit of algebra here and investigate. So first we'll break it up into a sum, and we'll try to pull out the x terms. So you could write something like x0, x, and then 0, y. And then you might wonder what to do with the 1. So for now, I'm just going to leave the 1 here. And we'll see in a minute, actually, this 1 is going to cause a problem that will lead us to conclude that this is not a subspace. But for now, we'll just leave the 1 there. So the question is, can we write this as some number times a vector? So we could write x101, but we run into problems with the second vector. See, we can't pull the y out of this. We can't write plus y times some vector. We'd be forced to write something like 1 over y here, and that's not allowed because you're looking for a vector of constants, not allowed to put any variables in our vector. So essentially, we can't fully perform this step here, and we're going to say this is not equal to x times something. We'd have to have a vector of numbers here plus y times something. There are no choices. There's no choice of possible numbers here that could make this true. And I could put set brackets on here just to make this logically correct. So this set of vectors that we had in the question cannot be written as a span. It cannot be written as some multiple of the first vector plus some other multiple of the second vector, where those vectors just have constants in them. So the answer to the question is no. And if you want to give a reason, you can say because the set S is not a span. So if you're following along in the notes, please just be aware page 4 has been deleted. So you will be skipping from page 3 to page 5. And that's intentional as you go through the notes. So next idea that we're going to look at, now that we have a sense of what a subspace is, something like a line through the origin or a plane through the origin, we're going to look at 3 important subspaces that are associated with a matrix. So let's say someone gives you a matrix, 3 subspaces that we can create from that matrix. So let's look at these one by one. First subspace is the row space. And by definition, what that is, that's the span of the rows. So remember, every time we say span, it's a set of all linear combinations of the rows. So meaning take all multiples of the first row, take all multiples of the second row, and then take sums of those things, etc. So the shorthand notation that we'll use for row space, we'll just write row of A. And in a similar way, we can talk about the column space of a matrix. So what that is, that's the span of the columns. In other words, it's the set of all linear combinations of the columns of that matrix. And the way we'll write that, col of A. And then finally, null space of a matrix. So null space of a matrix is the set of vectors x such that A times x equals the 0 vector. So null, often used just as a synonym for 0 or 0 vector. So null space, it's the set of vectors x so that you can multiply A times x to create this 0 vector. And that's where the name null space comes from. So it's a set of vectors here that satisfy this equation ax equals 0 vector. And we will write that null of A just for shorthand notation. So let's do a quick example here. And the intention of this quick example is just to help us absorb the definition of row space, column space, and null space. So we'll do 3 parts here. Okay, so let's say that we're given this matrix, this 2 by 3 matrix. First question is the vector 610 in the column space of A? Okay, well, let's remember what the column space is. It's the set of all linear combinations of the columns. So we really need to ask, okay, if I take a linear combination of the columns of this matrix, we just want to know, can we make the vector 610? So you could do this using Gauss-Jordan elimination, but because the numbers are fairly nice in this problem, you might even just be able to do this by inspection. So there are many solutions here to this equation, but one would be to take 0 times the first vector, so 0 times the first column of A, plus 3 times the second column, plus 4 times the third column, and yes, that will make 610. So because we can find a linear combination, the answer to the question is yes, 610 is in the column space of A. So part B, the question is the vector 1, 2, 5 in the row space of A? Well, let's think what row space of A is. It's a set of all linear combination of the rows of A. So now we're interested in these 2 vectors here, the 1, 2, 0 and the 1, 2, 1. And we want to know if we take a linear combination of those 2 rows, can we make 1, 2, 5? So again, you could solve this using Gauss-Jordan elimination. Your variables would be the C1 and C2. So you'd go C1 times 1, 2, 0 plus C2 times 1, 2, 1. And we're trying to figure out whether we can make 1, 2, 5. So with a little bit of row operations here, you can figure out that yes, this system does have a solution. And the solution looks like C1 equals -4, C2 equals 5. So that tells us, yes, we can find a linear combination of the rows of A that produce 1, 2, 5. So is the vector 1, 2, 5 in the row space of A? Yes. The third question is the vector 1, 2, 3 in the null space of A? Okay, so let's remember what the null space of A is. I'm going to write the definition over on the side here. So null space of A, it's the set of vectors x such that ax equals the 0 vector. So if we want to know, is this vector in the null space of A, the question really comes down to, is ax equal to the 0 vector? If it is, the answer will be yes. If it's not, the answer will be no. So it's just a matter of taking our matrix, multiplying it by our vector 1, 2, 3, we figure out it's not equal to 0 vector, so the answer is no. Now, before we can get into any real calculations for this section, we need one more definition. So we're going to say that a set B is a basis for a subspace if 2 properties are true. So just in terms of the notation here, B is what we're calling the basis, and S is what we're calling our subspace. And remember that when we talk about subspaces are things like lines through the origin or planes through the origin. So if you want, you can just have sort of a picture going here. Imagine that you're in R3, and imagine that your subspace S is just some plane through the origin. So I think that will help us with breaking down this definition. Okay, so the set B is going to be a basis for this plane here if two things are true. So first thing that has to be true, the span of your set B has to equal S. And second thing that has to be true, the set B has to be linearly independent. So B is going to be a very small set, typically just going to have one or two vectors in it. If your subspace S is a plane, then B is just going to consist of two vectors. And what needs to be true about these two vectors? Well, the two vectors, if we take all linear combinations of them, they have to create S. So essentially, this is sort of like saying the set B has to describe the direction vectors for the plane to make sure that when we take the span of these two vectors that we create everything in S. But it's a little more rigorous than that because we also need B to be linearly independent. So for example, we could not take three vectors in this set because those vectors would no longer be linearly independent. So let's, just in our picture, let's say the blue vectors are B1, B2, they form our basis. That's just to give a little intuition for what we're talking about here. So intuitively, your set B, or your basis, if you want to call it that, it contains enough vectors to describe S. So that's what the first condition here is saying. It's got enough vectors so that when you take the linear combination of those vectors, you create everything in your subspace. But it has no redundancy. And that's what condition 2 is saying. So your set is linearly independent, meaning there's no vector here that can be expressed as a linear combination of the others. A basis, in a sense, is just the right size. It's got enough vectors to describe your subspace, but it doesn't have too many vectors. So let's look at some quick examples of different subspaces and what a basis for those subspaces would look like. So we'll just call this a quick example and we'll do a few different parts here. So part A, let's say we're talking about all of R2. So classic example of a basis for R2 would just be the vector 1, 0, and 0, 1. So certainly if you take the span of these, you get all of R2. And we've also got no redundancy because neither of these can be written as a linear combination of the others. Well, you could choose 3, 4, 5, 6 as your two basis vectors. So if you take the span of these two vectors, you do get all of R2, but there's no redundancy because neither of these vectors is a linear combination of the others. And in fact, you could take any two non-zero vectors in R2 that aren't multiples of each other, and that would be a basis for R2. So a couple of examples showing what can go wrong. Okay, if you just take the single vectors 3, 4, that would not be a basis for R2. And what would go wrong is the first condition, because if you take the span of 3, 4, you're not getting all of R2. So this set is not big enough to be a basis. In part D, this set of 3 vectors here is not a basis for R2, and now it's condition 2 that goes wrong. These vectors are not linearly independent. So each of these vectors can actually be expressed as a linear combination of the others. The algebra might get a little bit messy, but if you were to check whether these vectors are linearly independent, the answer would be no, they're not. And on an intuitive level, you could sort of guess that they're not linearly independent because we've got too many vectors in here. So just to make this slightly more intuitive, really the two most common examples we're going to run through is that our subspace might be a line through the origin in either R2 or R3. So if this is our subspace S, then our basis is just going to consist of a single vector, and you could choose any non-zero vector that lies along that line to act as your basis vector. Doesn't matter what vector you choose, as long as it's not the zero vector, then that will form a basis for your subspace. The other classic example is if you've got a plane through the origin. So let's say we're in R3. We've got some plane through the origin. So your basis is going to have two vectors in it. Let's call them v1 and v2. And which vectors can we choose? Well, any two vectors that are non-zero and not multiples of one another. So v1 and v2, let's say like this. You wouldn't want them to be the zero vector because that would not describe a direction. And you wouldn't want them to be multiples of one another because then when you took the span, you would just be describing a line. So essentially you can boil the definition for a basis down to these two cases, and that's going to cover, let's say, 90 to 95% of the situations that we see. Occasionally we'll go up into higher dimensions, but most of the time we'll just be in R2 or R3. So now we're getting into the real core of this section. See, we're going to talk about the row space, column space, or null space of a particular matrix. But what we're going to do is find a basis for it. So we're bringing these two big ideas together, the idea of a basis and the idea of something like a row space. And we're going to do a few examples just to really help everything click. So let's say that we're given this 3 by 3 matrix A, and we would like to find a basis for the row space of A. So remember what the row space of A is. It's just the set of all linear combinations of the rows of A. What we want to do is find a basis for that set. So remember, a basis boils a subspace down to a very small set of vectors, usually just one or two vectors, that describe that subspace. So we really want a very concise description of which vectors are in the row space. That's what we're looking for. Okay, well, the rule for how to find a basis for the row space of a matrix is to use the non-zero rows of either the REF or our REF. Doesn't matter which one. So you want to put your matrix into REF or RREF, and then just grab the non-zero rows, and that will be your basis for your row space. So let's do that. Let's take our matrix A. If we go through the usual row operations, I think I'll just outline what the row operations are. So I've just skipped over the details here, but if you wanted to put this matrix into REF, here's the process that you would likely go through. And I would say just going to REF is sufficient here. No reason to go all the way to our REF. And to answer the question, what do we need to do? Well, just grab the non-zero rows of the REF. So we're going to write our answer like this. We're going to say basis for row space of A is equal to, it's going to have a couple of vectors in it, so 2, 3, 7, and 0, 1, -4. Okay, now just a notational point. If you're thinking of these as vectors, you could put commas in there. But if you're thinking of them as rows of a matrix, then you don't need commas. So really it's acceptable to write it either way, but I would say it's just cleaner without the commas. So I tend to just write it like this. So let's understand geometrically what we've done by saying that a basis for the row space of A is this. Let's actually draw a picture. So we're talking about vectors in 3D. We know that because they've got 3 components. And we're talking about what object we would create if we took all possible linear combinations of the rows of A. So are we getting, a line through the origin? Are we getting a plane through the origin? And specifically, how is that tilting in space? So we've now got the answer for that. These 2 vectors here give us our direction vectors, and because there are 2 of them, we know we've got a plane. So if you were to just graph the vector 2, 3, 7, let's say that looks something like that, and the vector 0, 1, -4, let's say that looks something like that, roughly, just to make a picture. So you're talking about a plane through the origin that has those 2 vectors as its direction vectors. That's our row space of A. So to make sure that we've absorbed our 2 new definitions, row space of A is the set of all linear combinations of the rows of A. In this example, it's a plane through the origin, whereas the basis for the row space of A is just a very short list of vectors. You can roughly think of those as the direction vectors for the row space of A. They must span your row space of A, and they must be linearly independent in order to be a basis. So we're going to do a few more examples like this, working with the column space of A and null space of A, and in each case, we're just going to figure out how do we build a basis. So we've concluded from this example that if you want a basis for the row space of A, you're going to use the non-zero rows of the REF or RREF. And for each type of subspace, there's going to be a different rule for how to build a basis. So now part B, we're going to talk about how to find a basis for the column space of A. It's still the same matrix A as we were working with before. So the rule is use the columns of A corresponding to the leading entries of the REF or RREF. Doesn't matter whether you're talking REF or RREF. The point is you look at the REF, you figure out where those leading entries are, and then you use those positions as a guide for which columns of A to grab. Okay, so let's see an example. We figured out the REF for this matrix in part A, so I'm just going to recopy that. Okay, and then in the usual way, let's go through the rows of this matrix and just circle the first non-zero entry in each row. So we are getting circles in columns 1 and 2. So the rule is telling us to use columns 1 and 2 of A. And that's going to form the basis for our column space of A. So here's what our answer is going to look like. So our basis for column space of A is equal to, we're going to grab the first column of A. So it's important that we're referring back to the original matrix here and grabbing the 2, 4, 8. As our first basis vector, and then second column of A, 3, 7, 17. So referring back to the original matrix. So this is very different than how we built a basis for the row space of A. For row space of A, just grab the non-zero rows of the REF. For the column space of A, you use the leading entries as a guide for which columns of A to use. And you always have to refer back to the original matrix and grab the appropriate columns to form your basis. Okay, so let's talk about this in a little bit more detail. First, I want to talk geometry. So remember what the column space is. It's just the set of all linear combinations of the columns. And that produces something like either a line through the origin or a plane through the origin. So in this case, it's a plane through the origin. And our basis vectors tell us specifically which plane through the origin it is. So if you made a careful picture here, you could graph the vector 2, 4, 8. Let's just say that looks something like that. Could graph the vector 3, 7, 17. Okay, so without doing too much detail, let's just say that looks something like that. And so that produces a plane through the origin. And that's our column space of A. So roughly speaking, you can think of the basis as giving you the direction vectors for that plane. So just a little caution that I wanted to draw your attention to. When we do row operations, those row operations change the columns of a matrix quite a lot. So if you do a row operation like go row 2 minus 2 row 1 or something like that, that changes the linear combinations of the columns. So that's why we cannot just use the columns of the REF or RREF. You might think, oh, it'd be so nice if I could just put the matrix in REF and just grab the non-zero columns. No, you can't do that because unfortunately row operations really extensively change the information that's in the columns of a matrix. So part C, we want to find a basis for the row space of A consisting of rows of A. And I've written the matrix A over on the right side here just for our reference. So this part here where it says consisting of rows of A, that means we want our answer to involve either 2, 3, 7, 4, 7, 10, 8, 17, 8, or some combination of these vectors. So we want our actual answer to be described in the language of the rows of A. So notice that this is different from what we did in part A. Let's flash back to part A. In part A, we found a basis for the row space of A, but if you look at our answer was 2, 3, 7, which was a row of A, but 0, 1, negative 4, which was not a row of A. So this 0, 1, negative 4 is not actually described in terms of one of the original rows of the matrix. So that makes part C a different question than part A. So the trick for this kind of question is to recognize that the rows of A are the same thing as the columns of A transpose. And so what we can do is we can rephrase this as a column space problem. We can say, let's find a basis for the column space of A transpose. And the reason we might want to do that is we saw in our previous example in part B that when you're doing a column space type problem, you're always referring back to the original matrix and grabbing vectors from that matrix. So if we rephrase it as a column space problem, we'll be sure that our answer will involve the original vectors. So I'm going to write A transpose over on the side just so we can see this in a little bit more detail. We're going to put A transpose into REF. The leading entries will be a guide as to which columns to grab, and then we'll have an answer like, maybe the first two columns, maybe 2, 3, 7, 4, 7, 10, for example. And notice that those will be rows of A. So let's just run through some of the steps here. So first thing you could do to A transpose is divide the first row by 2. Then once you've got that, you could go row 2 minus 3 row 1 and row 3 minus 7 row 1. So if you did that, that would get you to the following matrix. And if you then did row 3 plus 4 row 2, that's going to create a 0 row at the bottom of your matrix. And so that's going to put you into REF. So here's our REF for A transpose here. So now what are we supposed to do? Well, we're supposed to circle the leading non-zero entry in each row, and then we're supposed to use these positions as a guide for which columns to grab. So we're going to say use columns 1 and 2 of, well, the matrix that we're working with is A transpose. So you could say a basis for the column space of A transpose is, well, first and second columns of A transpose. So we'll just look back up at the top of the screen here. First column was 2, 3, 7, and second column was 4, 7, 10. And remember, when we say column space of A transpose, that's a set of all linear combinations of the columns of A transpose. That is exactly the same thing as saying row space of A. It's a set of all linear combinations of the rows of A. And if you wanted to just write these vectors horizontally instead of vertically, that's totally fine, because we never care when we're just talking about a vector, whether it's written horizontally or vertically. So some people might prefer to write it horizontally because then it looks a bit more like a row. Some people might prefer to just keep it as a column because then it's more clear that you've solved the problem using the column space of A transpose. It really doesn't matter how you give your answer. So what we've decided is that the first 2 rows are sufficient to describe the information that's in the rows of A. So that tells us that the third row of A is actually a linear combination of the first 2. Okay, so let's talk about the geometry here. So if you were to draw a picture of the row space of A, it would be a plane through the origin. It would have direction vectors 2, 3, 7, 4, 7, 10. So let's just say that's something like this. And we're describing this plane through the origin. So that's our row space of A. So what's important here is that this is exactly the same plane that we drew in part A. So let's go back to that picture. So here's our picture from part A where we drew the row space of A. Here's our picture from part C where we drew the row space of A. So it's really exactly the same plane. If we drew it super carefully, the planes would look identical. The only difference is just in what these basis vectors look like. So in part C, we're insisting that the basis vectors are actually chosen from the rows of A, whereas in part A, when we just said find a basis for the row space, we didn't care what the basis vectors look like. Just use any basis vectors that you like. So it was easy enough just to grab the non-zero rows of the REF for that. So here's a new matrix, and what we're going to do now is find a basis for the null space of A. So let's remember what the null space of A is. It's a set of vectors x, so that A times x equals a 0 vector. So the idea for solving this type of problem is you are going to solve AX equals 0, and each parameter in your solution produces a basis vector. And we'll see through this example exactly how that works. Okay, so we're just going to solve the homogeneous system. Got zeros on the right side, and we got our matrix A here. We're going to solve this in the usual way. So put this into REF or our REF. In this case, pretty fast to do. So in general, I would say go to our REF because it's usually easier to solve from that form. And let's solve this in the usual way. So we would circle our leading non-zero entries for each row, and then any column without a circle is going to get a parameter. So we'd say x2 here gets parameter s, and x3 gets parameter t. And then maybe I'll label our variables here. Let's just call them x1, x2, x3. So x2 and x3 have parameters. We can solve for x1 using the top equation. So x1 plus 4x2 plus 6x3 equals 0. So if you bring these guys over and you use the values of the parameter, you can say x1 equals minus 4s minus 6t. Okay, and then we can just write up our solution in vector form. x1 is minus 4 times s minus 6 times t. x2 is s, so that's 1 times s plus 0 times t, and x3 is t, so 0 times s plus 1 times t. Okay, now our instructions at the top of the problem said if you're trying to find a basis for a null space of A, solve your system, and then each parameter produces a basis vector. Okay, so this is how we write down a basis for the null space of A. We just grab the vectors that appear in that vector form. So in this case, there will be two basis vectors, -4, 1, 0, and -6, 0, 1. So let's talk geometry then. So we are in 3D. We're talking about the set of vectors x that solve AX equals 0. So that's formally called the null space of A. And we figured out a basis for that set. So let's think of these two vectors here as being our direction vectors, and what they're describing is a certain plane through the origin in space. So -4, 1, 0, let's say that looks like that, and -6, 0, 1. Okay, let's say that looks like that. So that's describing to us some plane through the origin, which is our null space of A. So any vector that lies on this plane is guaranteed to make AX equal 0. So next problem, let's find a basis for the span of these three vectors. So there are a couple of good ways to approach this. First way to approach it, you could define a matrix where these vectors actually go into the rows. So 1, 1, 0, 1, 2, 6, 1, 5, 24. And then you could phrase the problem as find a basis for the row space of A. So that would be finding a basis for the span of those three vectors. So let's call that method 1. Or method 2, if you decide you really like columns, you could define a matrix A, which has these guys in its column. So they are the original vectors, now written as the columns of the matrix. And so then you'd be phrasing the question as find a basis for the column space of A. Okay, now using everything we've learned from our previous examples, you probably remember finding a basis for a row space of A, generally considered easier. So I would say let's do method 1, because what do we do to find a basis for a row space of A? Well, we put our matrix into REF, and we just grab the non-zero rows. So let's put this matrix into REF. You could do row 2 minus row 1, row 3 minus row 1, and then if you did those steps, you would find the last thing you would want to do would be row 3 minus 4 row 2. And if you did that, you would find a 0 row at the bottom of this matrix, and you would find your top rows would be 1, 1, 0 and 0, 1, 6. So that's the REF, and all we need to do to find a basis is to grab the non-zero rows. So we would say a basis is 1, 1, 0 and 0, 1, 6. And again, it's up to you whether you express those horizontally or vertically, it doesn't matter. So we could even draw a picture just to make this geometric. So 1, 1, 0 looks like that. 0, 1, 6 looks maybe something like that. So we're getting this specific plane in space. And our original question was the span of 1, 1, 0, 1, 2, 6, 1, 5, 24. So if you take linear combinations of all of these vectors, what you get is specifically this plane. So now let's move on to a new definition. Let's say we're given a basis, which looks like this. Let's say our basis is V1 through Vn. So this could be a basis for all of our n, or it could be a basis just for a specific, let's say, plane in space. But you've got some basis, and what we're interested in is the coordinate vector of a particular vector with respect to this basis. So this is what we're defining, the coordinate vector of vector v with respect to basis b. I think I'll actually underline what we're defining, and then I will highlight the formula. So the notation that we're going to use, you're going to write down the name of the vector, and then square brackets, you're going to put a subscript just for the name of the basis. And what this is giving us is just a set of coefficients, C1, C2, Cn, where these are the coefficients that you use to build V. So this is called the coordinate vector of vector V with respect to B. I often think of this as the coefficient vector. So all this is doing is just encoding what coefficients do I have to use for these particular basis vectors to build V. So the problem is to find this thing, which in words we would read that as the coordinate vector of vector v with respect to basis b. And what we're given, a basis b, so that's a basis for R3. And we've got this vector here. So this would come up naturally in applications if you were doing a problem where these basis vectors represented 3 directions. Maybe you've got forces acting on space or something like that. So these are 3 directions that you care about. And what you're trying to do is figure out how to write a specific vector as a linear combination of these basis vectors. So that's something that happens in applications quite a bit. All right, so I'll just highlight the 2 given things, which are the vector and the basis, and how we go about solving the problem. You would set up a linear combination. So you would say let C1 times the first basis vector plus C2 times second basis vector plus C3 times third basis vector equal whatever vector you're trying to build. So put this into matrix form in the usual way. C1 times first vector plus C2 times second vector plus C3 times third vector equals, this is our vector V that we're trying to build. Put that into either REF or RREF. So in this case, we've gone all the way to RREF. And what we're solving for here are these coefficients, C1, C2, C3. So if you go through all the details, you'd find C1 is -2, C2 is 3, C3 is 4. And the way that you write down your coordinate vector, in general, you say, okay, coordinate vector of vector V with respect to basis B is just encoding these different coefficients. So geometrically, that's just like telling you how far do I need to go along the first axis, and then how far do I need to go along the second axis, and then how far along the third axis to build this vector V. That's what we're figuring out here. So in this specific case, coordinate vector of v with respect to b would look like -2, 3, 4. So that's just encoding your different coefficients that you need to use for the basis vectors to build your vector v. So last big idea that we need to look at in this section is the idea of dimension of a subspace. So let's say the dimension of a subspace S is the number of vectors in a basis for S, or you could say the number of basis vectors for S. So let's look at a quick example here. So let's say that our subspace is all of R3. So that's our subspace. If you were to write down a basis for that subspace, the standard basis that you would think about is just one unit along each of your coordinate axes. And the dimension is the number of basis vectors. So dimension of R3 would be 3. It takes 3 basis vectors to describe all of R3. Similarly, dimension of Rn is equal to n. Dimension for a plane would be 2. Takes 2 basis vectors to describe a plane. And dimension of a line is 1. So it takes 1 basis vector to describe a line. So what actually is dimension? It's the number of basis vectors that you need to describe whatever space you're talking about. So now that we understand what dimension is, we can finish tying together all the topics in this section just by talking about the dimension of the row space, the column space, and the null space. So let's define the rank of a matrix to be the number of leading entries in either the REF or RREF. And that allows us to say that the dimension of the row space of A is equal to the rank. It also means the dimension of the column space of A is equal to the rank. So rank is just a word that we can use for talking about how many basis vectors does the row space have and how many basis vectors does the column space have. So let me draw a little picture on the side here, just to highlight really 3 important concepts that we've talked about and to figure out how they all go together. So if someone gives you a matrix, you can talk about the row space of that matrix. That's going to be the set of all linear combinations of the rows of your matrix. And that's going to be a physical object like a line through the origin or a plane through the origin. So most typically it's a plane through the origin. So let me just draw it like this. Okay, so that's our row space of A. Now we've talked about how to find a basis for the row space of A. You use the non-zero rows of the REF or RREF. So let's say in a typical example, that might involve 2 vectors. Okay, sometimes it's 3 vectors, sometimes it's 1 vector, but let's just say for this example, it's 2 vectors. And we could draw those in the picture. So let's say this is V1 and that's V2. And now we've just introduced this new term, which is the rank. We talk about the rank of a matrix. And what that is, that's the dimension of the row space of A. So informally, just the number of basis vectors that it takes to describe your row space. So that would be 2. And however many basis vectors it takes to describe the row space is always the same as the number of basis vectors it takes to describe the column space. So the column space of this particular matrix is guaranteed to be a plane through the origin, but it will be a different plane than the row space of A. So I'm purposely going to draw this sort of tilted differently in space. So that's, let's say that's our column space of A. Guaranteed to be 2-dimensional because the rank of A tells us how many basis vectors we have for the row space and how many basis vectors we have for the column space. But the basis vectors for the column space of A will be different than the basis vectors for the row space of A. So I could call these, say, B1 and B2. They'll be pointing in different directions than V1 and V2 were. The nullity of a matrix A is the number of parameters in the solution to AX equals 0. So if you rephrase this, you could say the nullity of A is a number that describes the dimension of your null space of A. So again, just to make this one a little bit more geometric, let's say someone gives you a matrix A. Let's say you find all the vectors x so that ax equals 0. So that is your null space of A. And that's going to be a geometric object like a line through the origin or plane through the origin, depending on what your matrix A looks like. So let's say we're in three-dimensional space. Let's say our null space of A is, for example, let's say it's a line through the origin. So that's our null space of A. A basis for the null space of A is a set of vectors that concisely describe your null space. Specifically, they have to span it and they have to be linearly independent. So in this example, it would just be a single vector. And informally, you can think of that as just being a direction vector for your null space. Okay, and then we have this new terminology called the nullity, which is just talking about how many basis vectors do you have. So in this example, this little made-up example, it would be 1. So if your null space is a line through the origin, nullity will be 1. If your null space is a plane through the origin, nullity would be 2. So we've got this matrix A here, and we want to find the rank and the nullity of A. Well, let's think about rank first. So the rank is just the number of leading entries in the REF or our REF. So let's put our matrix into REF. If we go through this row by row, circle the leading non-zero entry of each row, up there would be 3 circles. So the rank of A is equal to 3. Okay, now let's think about what nullity is. Nullity is the number of parameters that you get when you solve the system AX equals 0. So just think nullity of A, if you want a keyword here, it's the number of parameters. Specifically number of parameters when you solve AX equals 0. And how do we get parameters? Well, they come from the columns without circles. So essentially you're just looking at the REF and figuring out, okay, how many of these columns don't have circles? That would be 1. So the nullity of A is equal to 1. So based on that discussion then, we can come up with a fact, and that is that for any matrix A, if you add up the rank plus the nullity, you're guaranteed to get the number of columns. And we sort of saw the reasoning why in that previous example. So if you put your matrix into REF and you go through the rows and you circle the leading non-zero entry in each row, every column is now either going to have a circle in it or not have a circle in it. Columns with circles contribute to the rank, and columns without circles contribute to the nullity. So if you add up the rank plus the nullity, you are guaranteed to get the number of columns. So to cap off this section, we are going to look at the fundamental theorem of invertible matrices. The statement is, let A be an n by n matrix. The following statements are equivalent. So what that means, take any square matrix, and when we say the following statements are equivalent, what that means is that statements A through O are all true or all false for any given matrix. So choose a square matrix, all 15 of these statements are true or they're all false. So I'm just going to break down what the statements are, and then we can talk about how to use them. So I would break them down into, these are the 5 statements that we saw in section 3.3. There are 2 statements that we won't see until chapter 4. So essentially don't worry about those yet. And then there are sort of 3 groups of other statements that we can now talk about. So one is F and G are statements about the rank and the nullity. Statements H through J are properties of the columns. So things like the columns are linearly independent, the columns span Rn, the columns form a basis for Rn, and then 3 statements about the rows as well. The rows are linearly independent, the rows span Rn, and the rows form a basis for Rn. If we look at F and G, F is a statement that the rank of A is equal to n. And that's actually, of all the things on the list, all 15 statements here, calculating the rank is what I would consider the easiest thing to check on this list. Out of all 15 properties, this is the easiest thing to check. So if someone gives me a square matrix, we can put that into REF quite quickly and just count the number of leading entries quite quickly and quickly determine, is the rank of A n or is it not, where n is just the size of the matrix. And if it is, then you know all 15 properties are true. If it's not, then you know all 15 properties are false. So just by checking the rank of a matrix, you're actually getting a huge amount of information about that matrix. So the question is this set of 3 vectors a basis for R3? Well, first thing I would want to do is turn this into a question about a matrix. So I'm going to build a matrix out of these vectors. We could either put the vectors into rows or into columns, but hopefully we've learned from this section that it's a little bit easier to work with the row space of a matrix than the column space. So for me, it would feel natural to put these into the rows of a matrix. And then let's calculate the rank of this matrix. And once we know the rank of this matrix, then we can use the fundamental theorem of invertible matrices to decide whether the answer is yes or no. Okay, so let's get this matrix into REF. I'm basically going to run through the steps without too much detail. So row 2 minus row 1 and row 3 minus row 1 would give us 1, 2, 3, 0, 3, 3, and 0, negative 1, 1. And then from there, a couple more steps, we could go row 2 over 3. And then once we had that, we could go row 3 plus row 2. So if we were to do that, here's our REF that would pop out, be 1, 2, 3, 0, 1, 1, and then 0, 0, 2. Okay, now rank of a matrix is the number of leading entries in either the REF or the RREF. Remember, when we talk about leading entries, we're always talking about row by row. So we just run through the rows of our matrix, circle the first non-zero thing that we see. And how many circles do we have? 3. So that tells us that the rank of A is equal to 3. So let's go back to our fundamental theorem of invertible matrices and see how that helps us solve the problem. So we had a 3 by 3 matrix, and we decided that the rank of that matrix was equal to 3. So statement F is true, and what that tells us is that all 15 of these statements are true for that particular matrix. Now the statement we're really interested in investigating is whether the rows of our matrix form a basis for R3. So because F is true, we can conclude that M is true, and that's going to give us the answer to the question. So let's go back to our example and just write down the details. So because the rank of A is equal to 3, that implies that the rows of A form a basis for R3. So let's look back at the question just to be sure that we are answering it. The question is this set of 3 vectors a basis for R3? So we put those 3 vectors into the rows, and we decided that yes, these rows do form a basis for R3. So the answer to the question is yes. So that's our video on subspaces and dimension. Thanks for watching.